Hey everybody. Sorry, my dog's gonna bark probably a few times. Theseus, go sit. Good boy. Settle. All right. Hopefully he doesn't bother us too much. Let me go ahead and get the slides pulled up here. All right. And I'm gonna rely on you guys to tell me whether you can see that. I cannot see you. Can you guys see this? I should be sharing my screen right now.
Yeah, I can see it.
Okay, good. If anybody cannot see it, let me know. Um, okay, so it's 4 o'clock and I'm going to go ahead and get started. So we're talking about phase diagrams and slope fields today. And these are something that we already saw in the last class, but there's a little bit more that we can say about them. So first off, we're going to talk about autonomous differential equations. And I mentioned these again in the last class, but again, we can say more about them. So a first order autonomous differential equation is one of the form this. And what's important to notice here is that this function f doesn't involve the independent variable t, right? And so ostensibly, they're always separable. You could say divide by f of x and then multiply the dt to the other side, and you get the equation or separated equation dx over fx equals dt. And then you can say, all right, well, if we integrate that, then we get a solution here. But the problem is that this function may not always be easily integrable. But what we want to do here is use the form of this equation to sort of qualitatively analyze the solutions to autonomous differential equations. Um, as an example, population models are usually autonomous because of this hypothesis that we had, that the population only depends on the rate of change of the population only depends on the current size of the population, maybe with some two-party interactions over here. But there's no t over there, no time dependence of the derivative. So these are always separable and so on. And what can we say about these? Well, we're interested somewhat in the constant solutions. We call these equilibrium solutions. And so I have this theorem here that says, given an autonomous equation of this form, a constant function like this is a solution locally whenever the right side of this equation is equal to 0 if you plug that in. Right? So this is some function, and you can plug values for x into that. And if you plug in a number instead of a function for x, and you get 0 out, literally the 0 function, then we call that guy a 0 of f, and it ends up being a solution of this differential equation. I say locally here because you could have non or discontinuous functions where they are constant on some interval, but most of the time you won't have to worry about those. It's just something to be aware of. So here we have a practice example. Find the equilibrium solutions of the following equations. I'm going to try this and see how it goes. I'll give you maybe 2 minutes to go ahead and try to find the solutions to these. So go ahead and take out a piece of paper, or if you're doing this on your iPads, use that and try to figure out where the equilibrium values of x are here. You can use this theorem.
Recording in progress.
Okay, so I think that's plenty of time. Has anybody figured out, hold on one sec. Has anybody figured out the solution to, or the equilibrium solution of the first equation? Okay, I'm going to take that as a no. So the equilibrium solutions are the ones where f of x equals 0. And what is f of x in this case? It's this thing. So if I set 6 minus 0.5x equal to 0, I can solve that for x and get 12 out as an equilibrium solution. And that's the only option, or the only value of x that makes this equal to 0. It's a linear equation, so we can solve it, and that's it. For the other equation, we do the same thing. So let me move this over here, and we can solve that equation. So we have the sine of x plus the cosine of x, and we set that equal to 0. If you rearrange this a little bit, you should get that the tangent of x equals -1. You can subtract the cosine to the other side and then divide by cosine of x, and then you have sine divided by cosine. And now the tangent of x is equal to -1 at a couple of different values. I think the easiest one to note probably is minus pi over 4. We have minus pi over 4. And then we also have multiples of, or that plus multiples of pi. So you go halfway around the unit circle and you get the tangent of that same, or that next angle is also equal to -1. So we have plus n times pi, where n is some integer. All those are solutions, equilibrium solutions for this differential equation. All right, so finding the equilibrium solutions is actually fairly easy for these, or most of these problems. You just set the derivative equal to 0 and then solve the resulting equation. So what do we really care about is the behavior of solutions that are nearby to these equilibrium solutions. If this guy is a solution, then the direction of motion for the solution, you sort of think of it as, well, we'll draw that in a second. You think of it as a point moving along in time. The direction of motion at any time is governed by the sign of that derivative, right? The sign of f of x. If the derivative is positive, then the function is increasing in time. If the derivative of f is negative, then the derivative of x is negative, then the function is decreasing. And so you can sum this data up in a single picture called a phase diagram. I'll draw a quick picture of one here before we go to the definition and draw an actual phase diagram just to give us the idea. So say we have an equilibrium solution here. Let's call this x0, and we'll have another one down here. This is x1, and then this is our t-axis and our capital X-axis. And let's say that the derivative, or f of x, is greater than 0 over here, and f of x is less than 0 over there. Running out of space a little bit, but all right, f of x is less than 0 over here as well. Well, then if I pick an initial value, say at time 0, my function has to be right there, then as I go to the right, my function should increase. Right? and it should increase and try to get closer to this equilibrium solution. Because if it hits that equilibrium solution, then it's got to be equal to that forever onward, because the derivative at that point is equal to 0. So once your solution is equal to this value x0, it doesn't change. If it's not equal to it, but it's down here, it's going to try to get closer to that value. And also note that it's trying to get further away from this value x1. Similarly, if I start with a value over here that might be very, very close to x1, and then I go to the right, my solution should try to get further away from this equilibrium value, simply because that f of x function is negative, and that tells me the derivative of x is negative, and so it goes down. Same thing happens up on top. Initial value over here, then your function tries to get closer to x0. Okay, so this is a big ugly picture of a phase diagram, and what we do typically is cut out all of the t-axis and just draw the x-axis over here. So let's look at a definition. A phase diagram, or a phase line in our case, is a drawing of the real number line where equilibrium solutions are marked by dots and intervals between the solutions are marked by arrows corresponding to the sign of the derivative. This is exactly what we did last time with one of our examples. So terminology, non-equilibrium solutions like the green lines that I drew over here, those are called trajectories. Again, you think of autonomous differential equations as describing a point moving over time. And why do we use phase diagrams? Because they're helpful for evaluating limits. That's one reason. But let's go ahead and try to draw a phase diagram for this differential equation. So if you want to try and follow along here, first off, we want to draw a horizontal line. And this horizontal line, make it straight here, this is our x-axis turned on its side. I'm going to go ahead and mark the endpoints here. These are minus infinity and positive infinity. So they're the endpoints of my real number line. All right. Now I have this differential equation right here, and I want to look at the equilibrium solutions. I want to know where they are so I can mark them on my diagram. That's what it says, real number line where equilibrium solutions are marked by dots. So I need to find those equilibriums before I do that. Okay, so f of x in this case is a polynomial. If I want to find where it's equal to 0, I just need to factor it. And luckily this one factors pretty nicely as x minus 4, x plus 3. Okay, so I have two equilibrium solutions, one at -3 and one at +4. Okay, now in between here, I have to check the sign of the derivative, right? Check the sign of this function. Where is it positive and where is it negative? I only have 3 intervals to check, and so I can just plug in some numbers here. So I have, let's say, try -4. If you plug that in here, then this term is negative, and this term is negative. So my derivative is positive right here, fx greater than 0. And so what that means is that I'm going to draw an arrow pointing to the right. Sometimes people like to draw double arrows here. Okay. So then what about the middle interval here? Well, same thing. I could plug in 0, and well, clearly there I'll get -12, which is less than 0. So I have fx less than 0. And now I want to draw my arrows to the left. So this is telling me, all right, near this equilibrium solution, non-equilibrium solutions, the trajectories nearby are trying to get closer to -3 on either side. Okay, what happens to the right of 4? Well, I compute my derivative again at, let's say, x equals 5. Okay, at x equals 5, this is positive and this is positive. So I have a product of two positive numbers is positive. All right, and so I get arrows going to the right again. And so now this is a phase diagram. And what this is telling me right here, I said it's useful for evaluating limits. Well, if x0, let's say x of 0 to be explicit, if x of 0 is less than -3, then limit as t goes to infinity of x of t, supposing I have a non-equilibrium solution, so my initial condition is over here somewhere, then the limit as t goes to infinity, well, that point's going to try and drift over towards this one. And so my limit is -3. Similarly, if my initial condition is, if it's greater than -3 and less than +4, then I also get a point over here, and that's going to try and drift over this way according to those arrows, right? They're telling me the derivative is negative, so the solution curves drift in a particular direction this way, back towards -3. And over here, I have the opposite. My solution curves are going to drift away from -3 and also away from 4. So we'll come up with some language to describe these in a minute. But these are, this is how we use phase diagrams in general. Okay. Do we need to see this slide for any longer or any questions about this so far? Okay. So moving on, we have an example here. We have a 100-gallon tank of water with a 0.2 pound per gallon brine solution. And this is poured into, or sorry, this 0.2 pound per gallon brine solution is poured into the tank of water at a rate of 4 gallons per minute. And then the brine is mixed as it enters and drains out at the same rate. So you never have the volume changing, clearly. 4 gallons in, 4 gallons out. But the concentration of the tank is changing over time. And so what do we want to know? What is the long-term concentration of salt in the tank? And then we want to draw a phased line illustrating that. Okay, so I'll give you maybe 5 minutes to try and work that out. So this is one of our mixing problems. I would say start off with our standard rate equation. So rate equals flow in minus flow out. Okay, start there, try to write a differential equation that models this situation, and then see what the limit is. See what the equilibrium solution is. Okay, let's come back here and try and solve this. So does anybody have an answer for me for the limiting value? What is the long-term concentration of salt? I just realized that I should also be paying attention to the chat here. Yes, Nathan, 12 was the correct answer. I did not see that earlier. Do you have a number for me here? Zero? Not zero. We do have brine going in, so we should have a positive number here. Does anybody have a differential equation for me? So what do we get when we start plugging things in using our standard mixing problem knowledge? We should have dx dt equals something. And let's let x be the amount of salt, by the way. Okay, so I'm guessing not. Let's go ahead and write this out. The derivative should be the difference in the flow rates. So flow in versus flow out. Flow in is always the concentration of salt in is 0.2 pounds per gallon, and then times the flow or the volume flow in, which is 4 gallons per minute. So this is the salt concentration, and this is the volumetric flow. And then what's going to happen over here is that we need to subtract out the salt concentration out, which is going to be the total amount of salt that we have currently, and then divide by the current volume. Okay, so that's our concentration. We call salt concentration in, and this is salt concentration out. Okay, and times our flow rate in. So volumetric flow in, or sorry, out. Okay, so the other thing that we have is that the volume flow in is the same as the volume flow out, so the volume is not changing. And so V of t is equal to 100 all the way through. And that lets us simplify our equation a little bit. So we get 0.8 minus 4x over 100. And we can write that as 0.8 minus 0.04x. Okay, so now I can find my equilibrium solution because I have a formula for the derivative here. And I solve that for x and get, let's see, I get, what did I get over here? I think I got 20. So 80 divided by 4, yeah, it's 20. So x equals 20 is our equilibrium solution. Let's call this x eq equals 20. Okay, and so we want to know what is the long-term concentration of salt in the tank. Well, I would hope it's this, except that's not the concentration, that's the amount of salt in the tank. So our concentration is the amount of salt over the volume. And so this is 20 over 100, or 20% concentration, so 20% brine solution. Okay, and so now we want to draw our phase diagram for this. So here's our real number line, and we want to put in our endpoints. and our single equilibrium solution, which is 20. So we have minus infinity, positive infinity, and the last thing that we need is the sign of the derivative. So this function right here, here's another way to do this, is a linear function, and it has a negative slope. So it should be positive to the left of its root and negative to the right of its root. Right? We have this function right here as a function of x looks something like that. So it's positive to the left, which means that we have arrows pointing to the right towards positive infinity, and negative to the right of 20, which means we have arrows pointing to the left towards negative infinity. Okay, so our non-equilibrium solutions, if they start over here, say at 0, because we have an initial condition of 0% solution, 0% salt concentration, we start over here, our solutions should increase in concentration towards 20 pounds of salt. And if we start over here, we have a solution that starts with a whole bunch of salt in it. Well, then we're draining out more quickly than we're adding in. And so our solution is going to decrease in concentration back towards 20. We're draining out more salt than we're putting in, is what I mean. Is the flow rate is the same in and out. Okay, and so this right here is how we use our phase diagrams. 20 for all initial conditions x is 0. Why is it 4x right here? Let's see. Well, that's because in the flow out term, I'm looking at the salt concentration out times the volumetric flow out. So the volumetric flow was the same as the flow in, 4 gallons per minute, same rate. And so I just put a 4 right there. That's where the 4 comes from. And the x comes from thinking of this as the concentration. So remember, this is a little while ago, but the flow in is always the concentration, not concentration in times the flow in. So this is the flow of x in, so this is the volumetric flow in. The amount of substance X coming in depends on the amount of substance X inside of the actual stuff flowing in, which is water, with salt in it. And so that's just how you measure this. And then that concentration is always the amount of salt stuff versus the amount of total stuff. Your volume V of water versus your amount of salt at time t in the tank. Okay. Any other questions about this example? Okay. Feel free to type in the chat if you have questions. I'll try to check it periodically. All right, so now we want to talk about stability. So this is a way of talking about different kinds of equilibrium solutions. So if you let me scroll back a little bit, remember back here when we drew this phase diagram, we had two sort of different kinds of equilibrium solutions. The -3 had solutions that wanted to go towards -3. Everybody that was nearby wanted to end up at -3. But anybody that was nearby the equilibrium solution 4 wanted to get away from them. Right? If you're right at 4, your initial condition is equal to 4 for this differential equation, then you don't move. The derivative is equal to 0. But if you're a little bit to the left, a little bit to the right, it's called being perturbed, then your derivative is either maybe a little bit negative and then it gets more negative, or your derivative is a little bit positive and it gets more positive, and you start drifting away from 4. So these are called attractors and repellers, or sometimes stable and unstable equilibrium points. Okay. So this is called stability. We care about how stable an equilibrium solution is. Do points nearby try to get close? Do they sort of wiggle around nearby and not really settle, or do they just try to get very, very far away from the solution? So we call an equilibrium solution stable if the derivative of f is less than 0, and unstable if the derivative of f is positive. Might have that backwards. I'm not sure. I'll double check that. So you can check stability by checking the sign of the derivative of this thing, which is the second derivative of x, the thing that you're interested in. So the idea is that solutions nearby to a stable point move closer to s, while solutions near unstable points move further away. And there's sort of an analogy that we can put in here, is that stable points are sort of like valleys, and unstable points are like hills. If I put a ball inside of a stable point or nearby to a stable point, it wants to get closer, right? Balls are going to roll down into this valley to try and get towards the bottom right here. But if I put a ball at the top of this hill, all right, well, maybe if it's perfectly balanced, it'll stay right here. But as soon as you kick it a little bit to the left or right, now it's going to go rolling all the way down the hill, right? Until it maybe finds another one of these stable equilibrium points. So this is the idea behind stability: stable and unstable, valleys and hills. So phase diagrams are just ways of talking about limits and talking about which limits you actually go to. So stable points, we might as well draw a picture of them so that we know exactly what we mean. On a phase diagram, a stable point, call it S, has arrows pointing towards it on either side. For an unstable point, call it U, you have arrows pointing away from it. So everybody wants to be near a stable point. Nobody wants to be near an unstable point. These aren't the only options, though. You can also have a semi-stable point. Sometimes these are called hyperbolic. Hyperbolic works a little bit better in 2 dimensions, but sometimes I like to use that terminology because it's a similar idea. So hyperbolic fixed points, or not fixed points, equilibrium points, or semi-stable equilibrium points, have one side where solutions go away from them and the other side where solutions go towards them. Okay, and these are these 3 now are essentially the only options that we have. You know, stable, unstable, or semi-stable for autonomous differential equations. Okay. And the last one is we have this example, and I'll just work through this one. So we have a standard autonomous differential equation. There's no t dependence over here. And we're given the graph of the derivative, right? We're given the graph of f, which is the derivative of x. So what we want to do is find the equilibrium values x and draw a phase diagram. Right? And then the last part is if x0, our initial condition, is 3, what is the limit as t goes to infinity? So this is a little bit hard to see. Let me zoom in for you. On this graph, we have a couple of different characteristics. We have like a maximum here, and a minimum here, and then it kind of races off to infinity on either side. So this may be like a cubic function. And here we have zeros. Well, what did that theorem at the beginning of class say? The zeros of f are the constant solutions. So what are the x values here? They are x equals 0, x equals 5, and x equals 10. So these are our equilibrium solutions. And then the last thing that we need to do is check, okay, what about in between these numbers? Is the derivative positive or negative? Well, with the graph, it's pretty easy to tell. We have minus, positive, negative, plus. Minus, plus, minus, plus. And so you can think of the x-axis here as literally the phase diagram. And so we can just draw in our arrows going to the right here, to the left there, and to the right here, and to the left there. So now, given this, we can start classifying our points. So we have, let's call this x0 equal 0 is, what kind of equilibrium point is this one? You're welcome to type it in chat if you have arrows pointing to the left over here and to the right over here, which means what about this equilibrium point?
Is it unstable?
It is unstable. Good. Yes. So we have arrows pointing away on both sides from x0. So this is unstable. Like maybe I should do that in red. Red feels like an unstable color. So this is unstable. And then this one right here, for the same reason, just in reverse, is stable. x0 is x0 equal 0 is unstable. x1 equal 5 is stable. And x2 equal 10, well, I can see over here that the arrows point away from it. So this is also unstable. We have no stable or semi-stable fixed points. I keep saying fixed points. No semi-stable equilibrium points here. If you wanted to get a semi-stable equilibrium point, you could take any polynomial with a repeated root. So let's say something like, I don't know, 2x cubed minus x squared. This factors as x squared times 2x minus 1, and it has equilibrium solutions at x equals 0 and 1/2. But this one is now semi-stable. Right? You can check the graph of this, but this will be one of those zeros of this function where the graph goes down, touches the x-axis, and then goes right back up. And then over here, it'll touch down at 1/2 again and go past. So this would be a semi-stable fixed point because it's degree 2, equilibrium point. Okay. And then I guess it says draw a phase diagram. We already did that. And if our initial condition is 3, what is the limit as t goes to infinity? All right, so what we do is we find 3 on the x-axis, probably somewhere around here. Look at the direction the arrows are pointing, and then keep going until we hit an equilibrium point. The one that we hit is 5, that's 1. That's our stable point, which makes sense. And so we can say limit as t goes to infinity of x of t equals 5 if x0 is 3, if we initially have 3 of whatever we're measuring. Okay. That's an example of phase diagrams. What happens when we don't have autonomous equations, when we have a t dependence on the in the derivative on the right side of this equation? F is not constant in t here. So we can't use phase diagrams anymore because things might change. The derivative might be positive and negative in a single region. If we go back over here, if f has a t dependence, then you can think maybe an extra axis here. This function might look different at different snapshots in time. And so we could have the function positive for some x regions and negative for some other xt regions. So the phase diagram analysis doesn't quite work the same. Instead, you can use something called a slope field. What is a slope field? Sometimes it's called a direction field. It's just a visualization of the solution curves. You basically take every possible point that you can compute by hand or get your computer to compute, plug it into this side of the equation, and then that tells you the slope of a tangent line at that point. Well, then you go over to that point in the plane and you say, all right, this has a slope of about, what is this, maybe 1/3, and you draw a little tangent line there, 1/3. And so now you can see your brain sort of tricks you into believing that these are like curves. So if you sort of follow along these lines, a solution should look something like this. Maybe I should use the drawing tool for that. Yeah, so maybe a solution looks a little bit more like this now. Okay. That's probably about as good as I'm going to get right now. Okay. So that's what a slope field is. It's just drawing the tangent lines at lots of different inputs. If those inputs are dense enough in the plane, you have lots and lots and lots of them, you can see these sort of curve-like shapes, and you can see that they follow the flow, essentially. Excuse me. And even if your differential equation is not autonomous, this one is, you'll still be able to see limiting behavior and equilibrium solutions if they're there. You can qualitatively analyze the solutions of the differential equation without ever actually solving it by hand. This is what you might do for a differential equation that is hard to do by hand. Come on. Okay. We'll just get to the next slide. It's freezing on me. Hold on. There we go. Okay. So what's the idea? So the slope field is basically the vector field given by this formula, which is the h is just there to sort of scale the size of the vector. But the y coordinate is telling you, okay, what direction should this vector point? So if I draw a little point here, well, then the vector should point in that direction, same as the slope of a tangent line. So we're just drawing slopes of tangent lines at every single possible point. And then if we give an initial condition, then we can follow those slopes to get and hopefully an approximation to a solution. Excuse me again. So here's the general non-autonomous differential equation, which is basically any first order differential equation where you can at least solve for the derivative. And so here's our initial condition. A solution curve might look like this. We don't know this ahead of time, but we can sample points all over the xy plane and calculate the slope there. I've probably said this a couple times at this point. Once you know that slope, you can draw these tangent lines right here. Okay, you pick a lot of regularly spaced points. That regularly spaced is actually fairly important. If you're not regularly spaced, you're just kind of randomly choosing points. It might end up being hard to draw a solution. When you compute the derivative of all of them, you start to build a picture of the shape of a solution. So here's an example of a couple of different options for this differential equation. This now is not autonomous. Okay. Typically, you'd have a computer do this and draw your solutions for you. They will end up looking something like this. Not quite what I want. Make that bigger. Yeah. There we go. So your solutions might end up looking something more like this or like this, but they should follow those tangent lines as closely as possible. Okay. Now, again, let's see if I got the links to work this time. Nope. Sorry. I don't know how to get those to work. So I have these on my computer here. Let me go ahead and pull those up. Okay, here we go. So now you should be able to see this. And it looks like, yes, that's what I can see on my other screen here. So we have exactly that differential equation that I mentioned was that was the slope field for. And here's how you might program that. You put in a horrible bunch of formulas here. Use this vector x. There's actually easier ways to do this. But the solution curve, this is what you might get from this actually solvable differential equation, would be something like this. And so remember, there's that constant of integration c. Let's look at what happens if I change the value of that. So as c goes up, the curve goes up. And as c goes back down, the curve also goes back down. Okay. So that slope field that got drawn, it really does give you the tangent lines to the solution curve. Okay, I have another one here. And this one allows you to draw any slope field that you want. Zoom out a little bit on this. Okay, and let's draw a different differential equation. Let's do maybe sine of y, and let's do the autonomous one that we did earlier. So cosine of y here, y0, y. Unfortunately, we have a whole bunch of different colors here. I don't think I can get rid of that easily. But here's our slope field. So it's drawn in rows, and all of these are supposed to be slopes of solution curves at different points. And then you can take this little dot here that has a line going through it, and that line will change direction depending on where you place it. And it should match the tangent line at any point, even the points that haven't been drawn. Okay. And so what happens for an autonomous DE is that you will have these rows where all of the slopes are exactly the same. What happens for a non-autonomous DE, if I change the formula I had over here, let's say maybe now we have sine of x instead of sine of y, now the rows don't look the same, right? But, sorry, the rows aren't the same all the way across, but I do have some sort of nice pattern behavior that I can see in here. Okay. Or if I change this to maybe x times cosine of y, see what happens there. Oh, okay, now I have something a little more interesting there. If I change it to x plus y, then I have this slope field. Solutions sort of follow the line y minus or y equals negative x and then go up. Or if they're a little bit below the initial conditions down here, then they start going down very quickly. And so we can have some interesting equilibrium behavior with non-autonomous DEs, where we don't really have equilibrium values, but we can have equilibrium lines in the TX plane. So the derivative is constant here. And when you go a little bit further away from that, then the solutions start getting pushed way out towards infinity, getting very, very vertical there. Okay, so I'm gonna switch back here and finish this off. We'll be done in just a minute. It's not working. Come on. There we go. Okay, so those are our graphs, and we have a couple more examples. I imagine you probably will want to be done, so I'll just go through these. Draw a slope field and phase line for the following autonomous DE, then compare the two. The phase line is probably going to be easier to draw. This is autonomous, so we can draw a phase line. So let's do that first. I'll do it up here. Or, yeah, let's do it up here. Our phase line has our standard minus infinity plus infinity, and then our two roots are going to be 5 and 0. All right. And then in between there, we'll have, let's see, minus to the left and plus to the right. So we'll have positive slope here, positive slope here, I think, and then negative slope over here. All right. It seems odd. If I plug in 6, this is negative, and this is positive. So that second one I drew was not correct. That should be the other direction. Okay, so we can immediately classify that as unstable and 5 as stable. All right, so what about a slope field? How do we do that? Well, again, you usually do this with a computer, but if you wanted to do it by hand, let's just see how that might work. You could choose a couple of points. And again, notice this differential equation is autonomous. So once I have a value of the slope for one value of x, I have it for that entire row. That's what we saw in that original slope field on Desmos. So let's say I plug in y equals 0. So y equals 0 gives me y prime equal 0 as well. So my slope field is going to look something like this. All of the solutions here should have horizontal tangents. Those are not really straight lines, but bear with me. All right, so, well, that was one of our solutions, our equilibrium solutions. So let's try something different. Maybe y equals 1. So if y equals 1, then we get y prime equals, okay, 1/5 times 4, so 4/5. Pretty close to 1. And we should have a slope that looks something like this all the way across. And these are meant to be more or less in the same direction. Okay, well, what if I skip up a little bit and we talk about y equals 4 now? So y equals 4, we get 4/5 times 1. Y prime also equals 4/5. And so we get the exact same row of slopes up here at up here around y equals 4. And then in between, you should have slopes that are a little bit more vertical. Something like this. But you can sort of see how tedious it is to do these by hand. So your solutions in between should do something like this. Get close to y equals 5, because 5 is that stable point. And then if you go down here, they should end up doing something like that, or maybe just going far away. Okay. So that's an example of drawing a slope field. Last thing that we want to talk about is isoclines. These are ways of drawing slope fields a little bit more quickly. And basically, they are places where the derivative is constant. So they help you draw those tangent lines a little bit more quickly when you don't have an autonomous DE. So you say, use the method of isoclines to draw a slope field for this differential equation. And then let's try and sketch a few solution curves through the field, just like we did for this differential equation. So now we have, I'm going to use the next page to do this. So we have dy dx dy dx equals x plus y. And the isoclines are where the derivative is equal to some fixed constant. Let's call it k. Well, then we have x plus y equals k. And if we focus on this equation, well, we can solve that for y and get y equals k minus x, or if you want to write it in, what is that, slope-intercept form, minus x plus k. So the isoclines in this case are straight lines with negative slopes of -1. And go. And so I can go ahead and draw some of those straight lines here. And the parameter k, this thing, is just controlling the intercept. So I can draw straight lines with slope of -1 going through all different possible values of k, all different possible intercepts. But one thing to note is that these are not, repeat, are not the slopes. These are just places where the slope doesn't change. So if I draw maybe a couple more here. That one, and then another one here. Okay. So these are not slopes of y equal y of x. What I can do is I can pick one of these values, say maybe this is k equal 3 right here for this top line. If k equals 3, then I have the derivative right here should be equal to 3, and that's along that line. Oh, okay. Well, now the derivative is 3. I can start drawing those slopes in. That's a very vertical line. So my slopes should be very vertical like this. Okay. And now if I go down to the next line, maybe that's k equal 2, my slopes are still pretty vertical, but a little bit less. And then k equal 1, my slopes are less vertical, but they're all the same along this line. And then for k equals 0, all of the slopes along this straight line are horizontal. And this is actually basically what people used to do before they had computers to do this for them. They would be a little bit more accurate about it than I'm being, but that's basically what they would do. Okay, here, let's see what happens at k equal minus 1. Now, at minus 1, the slope is minus 1, and that matches the slope of the actual line. So this is the only line where the slope of that line actually matched the slope of a solution curve. Right, and then down here, we've got more negative slopes, and just need the last one, which should be minus 3. Okay, that worked out fairly nicely. Okay, so now given this slope field that I've drawn using the method of isoclines, I can now take any initial condition, let's say x of, I don't know, x of minus 1, or sorry, y of minus 1, y of minus 1 equals, let's say, 1. And so that's my initial condition. And my slope there is 0. So as my function progresses to the right, it should be slope 0 and then start increasing and follow these slope lines. Okay. And then as I go to the left, it should start getting close to this equilibrium line of k equal minus 1. Right? So it's not really an equilibrium solution. It's not constant. But if an initial condition is right there, then the solution should follow that exactly. Right? The derivative. Okay, well, that's all I have for you today. So if you have any questions, I'll be here for a minute. And then if not, I will see you next week on Tuesday. You're welcome. First 2 minutes, could you go back to the autonomous slides? Yes, I can go back to the autonomous slides. Let's go back to those. Let's see. So we only had about 3 of them. We got this one, and then I'll post these right afterwards in a minute. I have my computer open already, so I can do that. Mm-hmm. You're welcome. So there's that slide, and then there's this slide. Okay, yeah, I'll post them in just a minute. Anybody else that's still on need any more of those slides? What does the y of -1 equal 1 represent in the last slide? That's the initial condition. That's just part of an initial value problem. So I set this example up as just a differential equation, solve this in general, which we could do. It's linear and you get some solution out of it. But if I were to make this an IVP, or an initial value problem, I would have to add in something like y of -1 equals 1. So I'm just picking a value to specify what the actual solution should be, because when I do solve this, I'll get y of x equals something, and then plus that constant of integration. That IVP part, the initial condition, is just fixing this value. That's telling you, okay, I have a whole family of solutions. This now tells me which one I actually want. And so in the picture, I'm just saying, all right, this point has to be on the graph of my solution, or this point has to be on the graph of my solution. Yes, exactly. Yes, you can use isoclines by picking that value k, and then using the tangent lines there as like a starting point for how to draw the graph. Right? And then as you go along, you just start following the rest of the isoclines. And so actually, if I were to draw, if I had, say, a different initial condition right here, maybe I said y of minus 2.5 equals, I don't know, 1 maybe. Then I would have an initial condition that's saying this point right here has to be on the graph, and so I should follow the curves down like that. Y of 1 equals 0. Yes, yeah. This initial condition was only for this graph. A proper initial condition for the one that I called an equilibrium would be more like this. Y of -2 equals 1, or y of -1 equals 0. Yeah, that would be a different k value. Mm-hmm. The line isn't necessarily flat; it's straight, but it follows the isocline in this case. Mm-hmm. Yeah, no problem. All right. Anybody else? Okay. Well, if not, then I'm gonna close the Zoom and I'll post these slides up for everybody to see, along with the ones that I haven't posted just yet, I think. All right.